Good morning, good afternoon. Welcome to our virtual symposium, Latin American Chemistry and Catalysis, brought to you by Chemistry Europe to showcase some of the excellent science developed by Latin American researchers. My name is Sandra González Gallardo, Deputy Editor of ChemCatChem and the European Journal of Inorganic Chemistry, and I will be your host today. Today, we have three outstanding Latin American speakers that will cover topics that include computational catalysis for organic synthesis, electrocatalysis, and energy materials. We will have Q&A sessions after each talk, so please enter your questions to our speakers using the question box. The moderator of this event is Iván Castillo, member of the editorial board of the European Journal of Inorganic Chemistry. He is professor of inorganic chemistry at the Institute of Chemistry of the Universidad Nacional Autónoma de México. He obtained his PhD in 2001 from the University of California at Berkeley, working in organolanthanide chemistry with Professor Don Tilley. His current research interests include the use of first-row transition metals for complexes inspired by copper monooxygenase, nickel iron hydrogenases, and iron vanadium iron molybdenum nitrogenases, as well as supramolecular systems based on calyx arenes. Thank you, Iván, for joining us and agreeing to moderate this session. The screen is yours.
Well, thank you, Sandra, and good morning and good afternoon to everybody connected and listening to this. I have the pleasure of moderating the session, and it is my pleasure to do this for Chemistry Europe. And now let's go to the main people that are making part of this, starting with Professor Osvaldo Gutiérrez. He obtained his bachelor's and master's degrees from the University of California in Los Angeles, and then completed his PhD in 2012 at UC Davis under the guidance of Dean Tantillo. His focus was on computational electronic structure methods to reveal mechanisms of catalytic processes. After this, he pursued postdoctoral studies with Marisa Kozlowski at the University of Pennsylvania. And afterwards, in 2016, he joined the faculty of the University of Maryland at College Park as assistant professor, was then promoted to associate professor with tenure. And very recently, in 2021, he was appointed professor at Texas A&M University, where he's at currently. His research combines computational and experimental approaches to advance the understanding of reaction mechanisms to aid the design of new catalytic transformations. Aside from these research interests, he's also passionate about increasing diversity in the sciences. So please, let's welcome Professor Osvaldo Gutiérrez. Thank you.
Well, thank you so much, Sandra and Iván, for this presentation. Can you all hear me? Just make sure.
Yes, we can hear you, Osvaldo.
Okay.
Go ahead.
Yeah, thank you. It's really a great honor to be part of this symposium. And today I won't take a lot of your time, but I want to basically tell you the story of what we've been working on in the past roughly 6 years on a project where we combine both the use of high-level computational tools and organic synthesis. So we do both in our lab to accelerate reaction discovery in organic chemistry. So an overview of what we're trying to do in our program is really shown here, where the idea is to get things that you could easily buy from chemical companies, and under the presence of base metals that we could tune by changing their properties, oxidation state, spin state, steric parameters, we could functionalize and add value to these compounds. And in particular, what we're really focusing on is on using iron and nickel chemistry to basically control these radical cascade transformations, in which you have a series of radical precursors under the presence of these metals. You're able to generate a radical, and controlling the fate of that radical becomes really crucial. As you can see, there are several different pathways that you can take, and if you're able to tune the selectivity of these transformations and control the anti-selectivity of these transformations, I think that'll be really powerful. How we do that is, as shown below, we combine both tools with the overall aim of really understanding the mechanism of these transformations. And in particular, we want to focus on understanding the factors that control the reactivity and the selectivity of these processes. If we do that, we think we're going to generate fundamental knowledge. And usually at this stage is when I typically, when I was working with Ken Haugen and Dean Tantillo, we published this work in collaborations with other groups. But now we want to take it a step further. We want to start making predictions and also validating those in our lab. So it's starting to basically new reactions. So let's think about this approach. Let's look at what exactly what do I mean of using computations to accelerate reaction discovery. A typical organic chemist, it faces a challenge as shown in the top, where they want to combine 3 different components. You have a series of different cocktails of reagents that you could try, solvent, additives, parameters, for instance, temperature, ligand, and so on. And the idea is that you want to select selectively to get product number 1. However, typically you encounter the challenge that you get more than just one product. You get a series of unidentified and unwanted products. And how do you go about optimizing for the particular product that you want? An organic chemist will go and change the parameters that you have. So change the catalyst, change the ligand, the solvent, the temperature, and then start playing around with a stoichiometry of A, B, and C. We do that in our lab, but at the same time, what we do in parallel is actually try to get the picture that we have down below, which is, can we map out the reaction coordinate using this model reaction to get how we get from the starting point to the final products? If we do that, and we have a lot of confidence that we're able to do that nowadays with the computational resources, then we could easily and rationally make changes to A, B, and C, to the starting reagents, not to the parameters that you could easily typically manipulate, for instance, the catalysts and the additives. So in this instance, let's assume that you want to cancel out or you want to raise the barrier of the product number shown in red. So what you need to do is identify the key transition state. So that's C shown here. And what you do is then in silico start making changes to raise the barrier of that process. If you're able to do that, then now you have a way to modify C to raise the barrier, and that presumably will shut down that pathway, and now you only have to worry about 3 other pathways. And then we do that for the desired transformation. Let's say that the P1 product, you look at what's involved in that key transition states, and then we do systematic changes in silico, and then we go into the lab and test those out. So now, as we're changing parameters that you could traditionally change, we're also making rational modifications to the substrates themselves to promote this transformation. So to put everything into perspective of the story that I want to tell you is that let's look at this compound here. Of course, a very important compound. It is made in a very large scale. It generates a lot of, basically, is billions of dollars in that sense. And typical disconnections to make this compound that's shown in green, where you make carbon and nitrogen bond disconnections. A more challenging disconnection is actually the carbon-carbon bond shown here, where you have not only an sp3 carbon-carbon bond, but also you have this new stereocenter. You need to control the net selectivity of that scent in that carbon. And that's very challenging. However, there's a long history of iron chemistry that you might be able to achieve this carbon-carbon bond and anti-selectively if you choose iron as a catalyst, because iron has been shown that you can engage a wide series of sp3 and sp3 hybridized nucleophiles and electrophiles. And even more recently, there's been several reports, very promising results where you could actually control the selectivity of some related transformations. For instance, this report by Nakamura, which you're able to form a new sp3, sp2 carbon-carbon bond with modest yields and modest selectivity. Some key mechanistic studies by Nakamura show that there's some evidence for radical formation. However, it was not clear the mechanism of this transformation. It was not clear what the iron species, spin state, oxidation state, or coordination number of that species is. So in a sense, optimization for this process relied on purely trial and error. So if we're able to achieve this goal, I think it's going to have broad implications to the way that we think and develop new medicines. For instance, here, more than 60% of carbon-carbon bond formations are really traditional cross-coupling reactions in which they use palladium in many of these cases. And as you can see, iron has several different advantages over palladium in terms of the cost, abundance, and toxicity. So with that in mind, what we want to start with is started this example. Can we understand the mechanism of this transformation? And naively, we went into this project, and as you've shown here, we're very fortunate that we burned basically most of our startup funds on studying the mechanism of this transformation. So whenever people think that computations are cheap, they're actually not cheap. They're very expensive. They're very time-consuming, very costly, and just like any other science, it's a lot of basically a lot of results that will lead nowhere, right? However, in this particular case, we found this catalytic cycle that's shown here. You could go into the details in this publication, but we found that the catalytic active species is an iron 1 species in a particular spin state, in the quartet spin state, with one ligand and an arrow binding to the iron. That species is responsible for activating the electrophile through this process shown here, where you have halogen atom abstraction to generate radical. And presumably here, the key thing that you want to do is be able to control the timing of the radical rebound into the iron. And that will be the anti-determinant step to generate the iron 3 species. We can then undergo reductive elimination to generate iron 1. And finally, you're able to restart the catalytic cycle upon addition of the Grignard reagent. This mechanistic proposal is very consistent with experiments in that a slow addition of the Grignard was required for the efficiency and selectivity of this transformation. And that makes sense in this case because this iron 2 species, what you want to do is control the timing of the radical rebound into the iron. However, if you have excess Grignard, that iron species will presumably undergo much faster transmetallation to generate the bis arrow species, and that will lead to unselected product formation. And also, this mechanistic proposal is consistent with experiment that the lowest energy diisomer transition state, as shown on the left, is actually the one that leads to the major enantiomer, and the one shown on the right is the one that leads to the minor enantiomer. And this interaction that I'm highlighting here in the gray boxes is actually the donor-acceptor interactions, and on the right side you have the steric interaction. Both of those interactions are consistent with mechanistic experiments and experimental observations in which the electronic nature of the Grignard had an influence on the anti-selectivity, and also the steric nature of the R group of the ester in the electrophile also had an influence on the anti-selectivity. Presumably, in one case, you stabilize the left transition state. In the other case, the steric parameters of the ester raises the barrier of the right disfavored transition state, and that will lead to greater anti-selectivity. So with this in mind, we published this report, but then comes the question, now what? How can this studies really accelerate reaction discovery? So we spent a lot of time thinking about more of the mechanism and doing more mechanistic studies that I'm not going to go into all the details. But basically what this led to is designing a new reagent, a new substrate, and showing the one on the left, that will promote a new and anti-selective radical cascade transformations. And hopefully, if you look at this substrate here, I can convince you this is not the first thing that you will try to test to develop a new transformation. So this is heavily based on mechanistic studies. And the idea is that we found that if you tether a vinyl cyclopropane, that will improve the efficiency of the system. And if you include an ester group shown here in the blue box, that would improve or lead to enant-selected transformations. So we made this substrate after several different steps, purifications and so on. And we tested this reaction, and as shown in the one on the top, presumably you undergo halogen abstraction to generate a radical. That will cyclize and undergo a radical cascade ring opening. Finally, you're able to trap that radical enanti-selectively. Of course, the 2A product shown here is a series of different diastereomers, so we oxidative cleave to analyze the product distributions. And as you can see, we indeed confirm that you're able to control this radical cascade and perform an anti-selective carbon-carbon bond formation. And as we could quickly advance the substrate scope of these transformations, and the fastest thing that we did is simply try things that were commercially available, so different Grignards, not necessarily go back to make modifications to the starting material. And as you can see, overall, you have good yields, good anti-selectivities for a wide range of systems. And the ones shown in the bottom, the ones with the electron poor Grignards, those are actually new Grignards that worked in these transformations that previously in the 2-component reactions did not work as great. So with this in mind, we submitted this paper for publication, and fortunately, and I will say fortunately, in this situation, it got rejected. So the main criticism of this paper was that no organic chemist is really going to make the substrates, that reagent shown in the top box, to make products shown in the bottom, because they're more simple. So nobody's going to go from more complex starting materials to less complex products. So in that sense, we decided to think about this a new idea. What if we have unlink the system, so remove the tether, so now you have that 3-component reactions rather than the 2-component reactions. And with the idea being that if you're able to form that radical presumably can undergo a radical addition to the vinyl cyclopropane and undergo a radical cascade, and you could trap this intermediate shown in the box on the top. After some screening of different conditions, we were very fortunate to identify this ligand. So again, this kind of highlights the need of using both computation and experiments. You have to take advantage of both tools to quickly advance science. So here, this particular ligand 2 would prove to be very useful in these 3-component transformations. And as you can see in the case in the bottom, now we're able to significantly increase the substrate scope of these transformations to include a wide series of different granular reagents, even new radical precursors, including those that have fluorines appended or those that lack the ester functionality, so esterically hindered tertiary systems. And as shown in the bottom, you could also promote an anti-select 3-component radical cascades with iron. And here, this is not optimized yields, but you can already see promising results, basically good in anti-selectivities, modest yields. And if I had another student, this would probably be a good project to continue evolving. So with that in mind, we started thinking, can we promote other 3-component transformations? And the answer is yes. We're actually very fortunate to find that these reactions, almost identical conditions, also work for other alkenes. So here we tested a series of different unactivated alkenes, which are still a problem in dicarbonyl functionalization. And we're able to find that this method tolerates a wide range of different alkenes. And again, as shown as before, you're able to tolerate that series of different radical precursors, including those that have fluorine groups on it. And again, we're also able to engage not the formation of these 2 different carbon-carbon bond formations, but also 3 carbon-carbon bond formations, as shown on the right, where you have this diene systems, and you're able to form 3 different carbon-carbon bonds. So with that in mind, we started looking at the literature. We started thinking, perhaps we have a system that is very robust that we might be able to exploit. So we started going back to what is known about iron chemistry. And what is known about iron chemistry is very good at generating radicals. But in a sense, if you look at the radicals closely, they're actually very limited. They're carbon-centered radicals, and they're surrounded by other carbons. There's some cases where you have different heteroatoms, for instance, this alkoxy system, or ester groups, as shown before, and you're able to trap those carbon-centered radicals with iron and do carbon-carbon bond transformations. So we got inspired by our collaborative works. Again, another area that I'm not going to discuss in detail. We collaborate extensively with many synthetic groups around the world. And we got inspired by the use of alpha haloboronates or vinyl boronates to generate a new class of carbon-centered radicals, those alpha boron radicals that have a boron next to it. In nickel chemistry, you're able to trap those radicals with nickel and do the desired carbon-carbon bond formation. So we thought, can we engage iron in this transformation, as shown in the bottom, and trap those alpha boron radicals with iron? If proven, this could provide a complementary approach to this nickel chemistry, and it might open up new opportunities for perhaps new systems that are challenging using nickel chemistry. So with that, we're able to actually use by slight modifications to the same conditions that we have. So again, this ligand proved to be very essential for this transformation. We're able to see that a wide range of different granules work in these transformations, including a series of different arrow groups, hero arrows, and vinyl systems that even work in these transformations. And those remain challenging using nickel chemistry. We also show that, again, as shown before, a series of different radical precursors, including those that have esterically hindered tertiary systems and even secondary systems working in this transformation. And what I want to highlight is the examples shown below, which are examples that nickel struggles to form. So now we're able to provide not just chemistry that nickel is able to do, but actually iron is able to do and show new reactivity. And I think that this could have profound implications for medicinal chemistry in rapid access to these compounds with perfluorinated or fluorinated systems. So with that in mind, we started thinking, can we engage more elaborate radical cascade transformations? And I shown the one in the left, we tried this different reagent, which is basically an alkyl halide with an appendant allyl group. This is commercially available. It could be a new radical precursor. And we want to see if we're able to promote this multi-component annulation cross-coupling reactions. And as you can see, without any modifications, we're able to get a one-to-one mixtures of those 2 different products. Presumably what you have is you have an iron species shown here in the catalytic cycle as A that undergoes halogen abstraction with your substrate 1 to generate this radical cage pair. And here, what you don't want is the radical to rebound to the iron. Instead, you want that radical to engage with the pi component. And it's well known that the carbon-centered radicals with fluorines are more sp3 hybridized, so they have a tendency to undergo much faster addition to pi systems. So in this case, it makes sense that you form intermediate number 2. And in that case, you're able to, you have divergent pathways here where you could have direct carbon-carbon bond formation of that radical, or this radical could undergo 5-exocyclization to generate a thermodynamically and less sterically hindered primary radical. And then that could also be trapped by the iron system and do carbon-carbon bond formation. So how do you go here about optimizing this transformation? One, you could do, again, you could change all the different parameters, or 2, you could change the substrate. So we can make the intermediate number 2, you could promote what you want is a 5-exocyclization. So you could change the properties of the alkene to make this process faster. And we could do that. However, we thought about, if we really wanted this favor just simply the dicarbofunctionalization, why not just simply dilute the system? Presumably that would allow in intermediate 2 to go to intermediate 3, and then we were able to trap intermediate number 1, thermodynamically more stable radical. And that's exactly what happened here. We're able to completely shut down the formation of the dicarbofunctionalization product and move into getting more multi-component annihilation cross-coupling reaction. So here's the MAC. I showed the burger because it reminds me of the, when I think of MAC, I don't think of this product, but I think of more about the little burger shown on the left. Nonetheless, we're able to show that this system actually works for a wide range of different alkene systems, including electron-poor, electron-rich alkenes, as shown on the top. It also works for exocyclic alkenes. We're able to form a series of new compounds, this 5-member rings, bicyclic compounds, or fused cyclic compounds that have a tetrafluoro-containing moiety. So why is this moiety not shown in medicines? Could that be important? And one of the things that I think I would argue that it hasn't been found or as active in medicinals is because it's really challenging to make these compounds. So if it's very challenging, pharmaceutical industry is not going to make, at least initially, would not attempt to make these compounds because there's no viable ways to make this. So hopefully this method here, this very easy, robust method to make this 5-member tetrafluoro-containing compounds provides a new route to test the properties of these complex products to perhaps have some bioactive activities. And we also show that again, yes, as a proof of principle, we show that basically you could vary the different grainures. You're able to tolerate a series of different grainures. And then this is not limited to this radical precursor shown on the top. You could also have tertiary systems with appendant allyl groups and also able to engage this radical cascade transformation to generate the product shown, this pyrocyclic compounds. And you could also engage these transformations in the presence of more complex, basically natural products or substrates like the one shown on the bottom right corner. So with this in mind, I want to finalize my talk to basically go back to our bread and butter. What is the mechanism of this transformation? And what is the role of this ligand in this particular that is able to promote this 3-component transformation? Why other ligands fail to achieve this transformation? So with that, some mechanistic study that we did on our lab is simply test are radicals involved? And the answer is very clear. Yes, we have very convincing evidence that the radicals are involved. So presumably by the one shown in the top example, you undergo halogen abstraction that engages in the radical cascade transformation. And at that intermediate, again, you have divergent pathways. We showed through computation that basically the ring open is much faster than the 5-exocyclization, and you're able to trap the primary radical. And that's exactly what we see experimentally. As shown in the one in the bottom, again, another more evidence for radical formation, which in the presence of either E or the Z alkene, you're able to get basically the same diastereomeric ratios. So with that, we decided to collaborate with one of the world's experts on iron chemistry, so Mike Neidig and Camila Aguilera-Cuenca, so shown here on the top corner. So here we want to test, again, why is this ligand so important in this transformation? What properties does it have that is able to promote this transformation? So one of the things that the ligand is able to do is that ligands, bisphosphonate ligands can coordinate to iron. One ligand can coordinate, or 2 ligands can coordinate, and there's many different basically ligands out there that have a presence for coordinating only one time to iron, or basically 2 ligands bind to iron. So what they did is this series of experiments where they have the pre-catalyst under excess amount of ligand, and they wanted to see the effect of the grainer in terms of potentially generating new species. So in the absence of grainers, so the one shown in the top, you're able to see only one species of iron. If you add one equivalent of grainer, that species completely transforms into a new species. I'm going to call it number 2. And then if you add another equivalent of grainer, then you're able to basically get a 3-to-2 mixtures of 2 different iron species. And if you let that sit up for a while, actually you start basically disappear in one and another species starts to appear. So what are these species? So what is the coordination number, the spin state, the oxidation state of the species? We're able to, Camille is able to get basically structure information, and we're able to assign the spin states of these transformations. And as you can see here, this is a gold mine for computational chemists, because one of the things that we always get asked is, why don't you use multi-reference computations of these transformations? They're better than DFT. And the answer is they could be better than DFT, but they're not practical. Not practical at this, basically with this level of complexity. We have to consider many different species, many different conformations, many different spin states, and so on and so forth. So we really have to rely heavily on tight collaboration with experimentalist groups. So from here, we're able to basically calibrate, use this information to calibrate our computational methods to see if we can able to replicate the structure parameters, the spin parameters, and then from there we have basically a justification for why we're using a particular DFT method to do more computations. And overall, what I want to highlight from this species here is that you only have one ligand. So this ligand has a steric parameters that only allows for one ligand to be bounded to the iron at any given time, even under excess iron species. And the key thing here is that now that we want to ask is, which of this species is responsible for, one, activating the electrophile, so generating the radicals, and two, which of this species is responsible for trapping the radical? If we have that kind of level of information, now we might be able to go back and start designing, making rational modifications to this ligand to promote new transformations. So to answer the first question, we, Mike Neidig and Camilla basically designed this experiment where they have a mixture of these two species shown on the left. So the mono arrow and the bis arrow species. If you subject those to electrophiles, so 20 equivalents, so that's supposed to mimic basically the catalytic conditions, which of this species is reactive with electrophile? And what it was shown is that the most reactive species is really the bis arrow species. The bis arrow species completely converts to this iron dihalo species, and then basically the mono arrow is not reactive. So this conclusively shows that between those two species, if you have a competition, the bis arrow species is much faster, orders of magnitude much faster to undergo halogen abstraction to generate that radical, and that presumably undergoes reductive elimination to generate a bis arrow species that is also observed experimentally, and that could then the iron one do under halogen abstraction, and then that would generate the bis halo iron species. So again, we use this information to also calibrate our computational methods. Now if we model the iron mono arrow, the bis arrow species, and try to understand the rates between those, now we have a method to basically calibrate our computations to continue our exploration. So with that in mind, we did that, and what we found is consistent with all experimental data that we found. You have a generation of the radical, the turbidiol radical, that could undergo rapid G's addition, so addition to the alkene to generate an alpha border radical. And that alpha border radical is extremely fast to be trapped by the iron species, but also reversibly. So that could open up new, basically, opportunities for rational design, because this radical can add to the iron and dissociate quickly. And if you have that kind of equilibrium, you might be able to control the carbon-carbon bond formation. So we, as shown here on the right, TS3, basically the lower energy transition state is to this quartet spin state. So this calculation showed that carbon-carbon bond formation in this transformation is spin selective to the quartet spin state to do carbon-carbon bond formation. The other spin states are much higher in energy, and actually I want to highlight TS number 4, where in the success spin state, in the higher spin state, it actually completely changes the mechanism. Now you go through a more outer sphere rather than an inner sphere carbon-carbon bond formation. And that could have implications if you're able to lower the barrier of TS4 rationally, so promote more of the success spin state, and I think we have an idea how to do that, then you might be able to engage more bulkier system because they go through a more dissociative type mechanism. So with that in mind, now we have what we think is basically a mechanistic proposal that before, I said one of the problems with iron is that the mechanism of this transformation was not known. Now we have extensive evidence for this mechanistic proposal shown on the bottom. And then we also we cannot rule out the other pathway shown on the right, where presumably an iron 1 species is responsible for halogen abstraction to generate an iron 2, and that could perform this catalytic cycle. So we're still continuing exploration of this mechanism. Again, we want to differentiate, do we have the mechanism shown on the left, or we have the mechanism shown on the right? Because if we have that kind of information, I think that will lead us to more rational design and new transformations. And as you can see here, this is not limited. So we have a whole program. I'm not going to show many of the different results that we have, but basically we can engage a wide series of different pi components that we're able to basically form new radical precursors of this alpha alkoxy radicals and trap those radicals. So here's some results that are already being published by Madam Rotella, that is now a postdoc at UPenn. And we're also able to show that the other ligand, the other chiral ligand, is also be able to engage in these 3-component transformations and get modest and selectivity. So the key thing that we want to highlight is that what is special about this chiral ligand that is also able to promote an selective transformations. I think we understand that part, but it's also able to promote the 3-component transformation. So it's behaving more like the ligand on the top. And I think we have some very exciting results on that area that we hope to share very soon. So with that, I want to acknowledge my group, both at the University of Maryland and currently at Texas A&M, the postdocs are working on this project, especially Lei Liu that started a lot of this chemistry, and Wesley that is now a postdoc at NIH, the source of funding. And I want to thank all of you that for participating and be here. I'll be happy to take any questions. So hopefully this convinced you that merging computations and experiments could provide a way to accelerate reaction discovery in this very challenging transformations. And with that, thank you, and I'll be happy to take any questions.
Thank you, Osvaldo, for a very interesting talk. The floor is open for questions. I can start with one. And I noticed that at the beginning of your talk, you mostly used iron ACAC with iron 3. And then when you showed us the Moss-Bauer studies, you started with iron 2. So I wonder what different species you might get from those reactions with the diphosphines to get to the intermediates that you think are involved in catalysis. What can you?
Yeah, exactly. So one thing that I will mention is that basically we tried a series of different pre-catalysts, and you can engage basically iron 2s and iron 3s at basically iron ACAC, and the yields changes slightly, but they don't have drastic effects. So those do work. We just, for simplicity, we just decided to go with the ones that gave you the best yields. But in reality, the pre-catalyst doesn't have so much an effect in terms of the efficiency of these transformations. But we do see that what they have a drastic effect is actually an selectivity. I'm not showing those results, but I think those are very exciting, where the pre-catalyst, so it might be like you mentioned, different species that are generated in situ. And when you have a chiral ligand, that might be able to basically generate a wide range of different iron species that might lead to unselective transformations. And what you want to do is really have a more controlled system where you generate only 1 or 2 different iron species, one that could engage with basically generating the radical, and the other one that could trap the radical. And you're able to do that, then that will lead you to more selective transformations. But so far, the pre-catalyst does not have much of an effect in terms of the yield, the efficiency, very minor, but it does have an effect on some of the selectivity that we see, and that's still ongoing on. But yeah, I agree that it could definitely change basically the formation of different iron species. And Mike Nidings has done some preliminary basically mechanistic studies on that, where they show the pre-catalyst does have an influence in terms of the rates of transmetallation. So that I think that in a sense that could change basically this catalytic cycle shown here.
Okay, well, thank you. Are there any other questions from the audience? Well, I think it's maybe early in some of our countries. And
yeah, but if they have any questions afterwards, they could always email me, or I'll be here basically through the chat. I could also answer questions on that.
Mm-hmm. Okay. Well, actually, if nobody else has a question, I do have another one. I don't know if I caught that. And also with the intermediates, did you have an iron 0 complex with the 8-6 coordinated? Yeah. So that's interesting. What role do you think those types of intermediates might play?
That we think that basically this iron 0 species, that the one shown on the very bottom, I think that one could basically dissociate, so decomplex the bi-arrow species, and now that species could actually engage with alkyl halides and activate those alkyl halides. But that, of course, now you're going to have a mixture of different iron species going on. So the key thing is how do you control only having 1 or 2 species in solution? And that's a key challenge. But I think to do that, we need more mechanistic studies. But I think one of the things this iron species here that we have not played around in terms of the reactivity, but I want to explore more is basically how fast can that activate the alkyl halide? Can that iron species also trap other series of radicals? And if so, what is the fate of those radicals?
Okay. Well, thank you so much. Hold on, maybe we have a question here from Chandra Leka. Whether the nature of iron species, its oxidation state, can it be identified using theoretical methods alone?
Yeah, you can identify that. You can assign them, but I think I would argue that you really need extensive, and I mean extensive collaborations with experimentalists, because any DFT method in reality, they basically could predict anything to be lower in energy. So if you just focus on, let's say, a species number 1, like here shown, the tetrahedral high spin, and if you use different functionals or different basis sets or different multi-reference methods, they're all going to predict basically different species being the lowest energy, whether that's the low spin, medium spin, or high spin. So what you really need is get as much experimental data to then calibrate not just one species, but several different species that you've seen that they're active or they're relevant in catalysis. And then that way, if you're able to mimic and explore that, then you're gonna be okay. But I think just focus on purely computational is not gonna be practical, not for this transformation, because I think everybody knows that the method, the spin states are very sensitive to the methods.
Okay. Well, thank you so much again, Osvaldo.
Yeah, thank you.
Oh, hold on. We have another question. People are now waking up. This is from Ronaldo Moura. Thank you for a nice presentation. Could you talk more about how or if chemical bond analysis methods could help improve the mechanistic insight?
Yeah. I think basically the more that you understand and know and are aware of experiments, different ways to analyze experimentally the species, and also computationally, the better you're going to be in terms of understanding really what's responsible for the observed reactivity. So I think in that sense, I think merging both is really crucial to promoting new transformations. So, and that will provide basically going more, and we have not done that, basically going deeper into this, this species even shown here is like, why is the high spin preferring these transformations? How high energy is the medium spin? And understanding a lot of those factors, I think, will become crucial. And I think that's where computations can really come into play in analyzing more of the bonding, more of the structure, electronic parameters, something that is really extremely challenging to do experimentally. So this crystal structure shown here actually took a number of months, I think even years to generate. So they're not easy to work with. They're very challenging transformations. But I think that's when also computations can really provide a lot of details, more further details about what could be going on with this iron species. And I think we're in the right time to start doing those computations, something that was not practical, let's say 10 years ago, and something that I think the next 10 years is going to be even better because we have more computational resources, and now we couple with machine learning to do a lot of these techniques that will speed up this process, and now we're in the right time to analyze very complex mechanisms of iron.
Okay, well, thank you again, Osvaldo. I think that now we need to move on to our next speaker, but thanks again.
Thank you.
Great talk. And we're going to move on to our next presenter of today, who is Ana Flávia Varela. She obtained her bachelor's degree from the Universidad Nacional Autónoma de México in Mexico City. And afterwards, she moved on to Universidad Autónoma de Madrid to get her MSc studies. And then she obtained her PhD in 2013 at the Technical University of Denmark, working on electrocatalytic reduction of carbon dioxide. She continued pursuing this field during a postdoctoral stay in the group of Peter Strasser at the Technical University of Berlin from 2014 to 2016. And towards the end of that year, she joined the Institute of Chemistry, the same institution that I'm at UNAM, the National University in Mexico City. And her research interests now include the synthesis of new electrocatalysts and the study of these catalytic processes in fuel cells and electrolyzers, with emphasis on CO2 reduction to syngas and hydrocarbons. So I'll leave the floor for Ana Sofía. Thank you. And please go ahead.
Thanks, Ivan, for the presentation. And also I want to thank Chemistry Europe for the opportunity to present my work here in this symposium. Are you seeing my screen now, just to check?
Yes, we can see it. Perfect.
Okay, so as I said, I'm really happy to be here. I really appreciate having this virtual symposium because I truly believe that this is a new way in which we could start to interact with scientists from all around the world. So I'm really looking forward to talk to you a little bit about what I'm doing in terms of the CO2 electrochemical reduction. That, as Ivan mentioned, is what I've been focusing for most of my career since my PhD. So why do I think this is an interesting process to study? I think it's, I don't need to convince anyone in this audience that we really have an issue with the CO2 concentration in the atmosphere. So we need to think of options of how we can reduce its concentration. And the obvious one is try to stop using fossil fuels so we can reduce the CO2 emissions we have. But there will be a process that is not so easy, so for which we don't have really carbon-free options, and like many industrial processes like cement or so, where we will continue to emit CO2 at least for the near future. So we need to find options of how can we deal with this CO2. And as a chemist, what we can think of is let's start to develop processes that allow us to convert CO2 into other useful products. Another, and maybe one of the things that comes as one of the most popular options to reduce our CO2 emissions is to migrate to renewable electricity. So solar and wind electricity, which are certainly good alternatives to produce energy without emitting CO2. And they are actually competitive in terms of its efficiency and the cost that they have. But they have a key challenge, and it has to be that these are not constant sources. So the electricity production will be dependent on the weather conditions. This is an old graph, but I like it a lot because it illustrates this point very well. So what we are seeing here is that the electricity production from wind and solar in Germany during the month of June changes a lot between day and night, but there are also some days where we produce a lot of electricity, or they produce a lot of electricity. There is days that are extremely sunny or extremely windy, where we have an excess of electricity. So if we really want to be dependent on renewable sources, we will end up in points like this where we will have a lot of electricity and we need to figure out what to do with it. So we need to figure out how to store it or how to use this electricity to drive, for example, to drive chemical reactions. And this is exactly what I'm studying. So let's try to use some renewable electricity to convert CO2 into some useful products. This will be taking place in a setup that, like the one I'm showing here, this is a CO2 electrolyzer. And at the anode, we will have what we call the oxygen evolution reaction. And this is a reaction where we split water to form oxygen. And we also generate protons and electrons. These protons and electrons migrate to the cathode. And this is where most of my studies focus at the moment. And it has to be with the reduction processes. So at the cathode, we could have just the reduction of protons. And this would be what we are, I think most of us are familiar with water electrolysis, where we would see the evolution of hydrogen. But when we're studying CO2 reduction, the evolution of hydrogen is our competing process. What we actually want is that these protons interact with CO2. So we see some carbon-based products. For example, we can see formic acid, CO, or even hydrocarbons. This is what most of my research is focused on, and as I will talk to you today, I've been mostly focused on these carbon-based materials as catalysts. These are materials made of abundant elements, so mainly carbon, but also nitrogen and some transition metals, for example, iron, nickel, or cobalt. These are certainly, as I hope I showed you today, these are certainly interesting materials for this catalytic process, but they are very heterogeneous materials. So we don't really, it's not easy to identify the nature of the active site on these materials. And for that reason, in my group, we have started working with MOF-based electrodes, which have the advantage of having very well-defined active site, and that we can tune this active site by choosing the proper building blocks for the MOFs. But we will have other challenges in terms of the conductivity of these materials. Once we have studied the catalyst for the cathode, we don't want to start to focus only on the cathodic process. We want to think of the whole electrolyzer, and for that we're working in this 3D printed electrolyzer that we design ourselves and that we 3D printed in collaboration with the University of Nottingham. And where we are starting to carry on some tests on this gas diffusion electrolyzer. So we will have one of these catalysts at the cathode side, but we also need to develop catalysts for the anode, and there are some students also working on that part in my lab. But today I will be focusing in mostly on the cathodic catalyst. So as I said, the main focus on my talk has to do with this what I call carbon-based catalysts, and what I mean by that are these carbon materials that we told to incorporate different nitrogen functionalities, and then to these nitrogen functionalities we can have the coordination of some metals. As I said, we look to have abundant metals, for example, iron, nickel, manganese, cobalt, or copper are some of the choices we can use to keep this catalyst made of abundant elements. This is something that I started working on during my postdoc, and what we did is tested different materials, the same family of materials, but with a different metal center. And we see that the product selectivity is highly dependent on the nature of the metal. And we identified two metals are probably the most promising to be used for CO2 electrochemical reduction. So namely iron. Iron can reduce CO2 at quite low of a potential. This means I don't need to give a lot of energy to the reaction to take place. And we can form CO with a decent selectivity. And we can also form traces of methane. These are very, very small amounts, but we could think that we can design the iron sites to enhance the selectivity towards methane. In addition, if we want to reduce CO2 selectively to CO, maybe we can think of nickel as a selected metal, because it has a selectivity of higher than 80% when we use it for CO2 reduction. So I started working on this class of materials when I came back to Mexico to work at UNAM. And the first thing we did is try some of these catalysts based on polyaniline, and we just change a little bit the structure of the material by changing the synthesis temperature. So we went from 750 degrees to 1050 degrees Celsius for the synthesis, and we characterize the resulting materials. What we observe is that the structure of the material changes a lot with the synthesis temperature. If we look with XPS to the concentration of different nitrogen functionalities, we clearly see that the concentration of pyridinic nitrogen, for example, decreases with synthesis temperature. By contrast, the concentration of graphitic nitrogen and nitrogen coordinated to iron increases with synthesis temperature. So we can see that the possible active sites are changing with the synthesis temperature. In addition, when we look at the active area of this material, we see that it's also changing with the synthesis temperature. In particular, we see that a higher synthesis temperature leads to a decrease in active surface area, which is a negative thing for catalysis. Once we had characterized these materials, we started doing some electrochemical testing. The first electrochemical testing that we normally do is cyclic voltammetry, where we compare how the reduction currents are in the absence of CO2 and in the presence of CO2. So what I'm showing you here is just the current in an aqueous electrolyte of the 5 catalysts saturated with nitrogen. And we see that in all cases, we have some reduction current, which can be attributed to the competing process of the hydrogen evolution reaction. We also see that the catalyst prepared at the lowest temperature has the lowest activity. And then there is a decrease, sorry, it has the highest activity. So we have the highest current when we prepare the catalyst at a lower temperature. This is attributed to the fact that we have a higher surface area, resulting in more activity. Once we bubble CO2 to our electrolyte, we see an increased current. And this increase in current is correlated to the reduction of CO2. So we see that all of our catalysts are actually reducing CO2, but they're also having some current that can be attributed to the hydrogen evolution reaction. We also see that the catalyst prepared at the lowest temperature is the most active, whereas there is a slight decrease at higher temperatures. To figure out if this current is attributed to CO2 reduction or hydrogen evolution reaction and which products are we forming during this process, we did some product quantification, and what we are showing here is the product quantification after CO2 electrolysis. And we did see that it also has an effect, so the synthesis temperature also affects the selectivity of the process. What we observed is that when we prepare the process, the catalyst at a higher temperature, we reduce the selectivity towards hydrogen evolution, and we enhance the selectivity for the production of carbon-based products, so namely CO and methane. We want to understand this in terms of the active sites presence, and what we see is that this increase of nitrogen coordinated to metal and the decrease of pyridinic results in a higher selectivity towards CO2 reduction. I'm pointing these two sites because as I will talk to you later, these have been proposed as the active sites in this carbon-based material. So it would seem that by having a higher synthesis temperature, we are having a greater number of iron coordinated to nitrogen, which has a positive effect on the selectivity of the process. This is a strong indication that the iron sites are the predominant catalytic sites in these carbon materials. To confirm this, we prepare an iron-free catalyst, and this is what I'm showing you here. So we have we characterize the electrochemical surface area, and we see that it's basically the same for the iron-free catalyst. But when we look at the current during cyclic voltammetry, we see that when we have iron, the reduction current is considerably larger. In terms of selectivity, here we see the selectivity of the process on the iron-free catalyst, and we see that although in the absence of iron, some CO2 is being reduced to CO, the main product is hydrogen. So what we can see here, or what I hope I show you with this first type part of my talk, is that these carbon-based materials are interesting catalysts for the CO2 reduction, but that their catalytic performance is highly dependent on their composition. And this could be tuned by the synthesis condition. In particular, what we looked was the synthesis temperature. And the synthesis temperature has, and when we increase the synthesis temperature, we have a negative effect in the loss of active surface area, which results in a lower activity. But we have a positive effect that we are introducing more iron coordinated to nitrogen, which is probably the predominant active site. Yet, even though we do see this, we still have a lot of questions remaining regarding on how the actual active sites look in this type of materials. For once, even though the metal is probably the predominant active species, we don't know how it looks like. So if it's coordinated to 4 nitrogens, as we usually draw it, so as we propose it is, but it could be also coordinated to a different amount of nitrogens, and there could be some vacancies that could be key for the catalytic process. In addition, we see that it's not only the metal that is being involved in the catalytic process. So we should also be aware that in this type of materials that are very heterogeneous, we can have more than one site contributing to the reduction current. And this is something that I want to briefly mention because we saw something that we were not expecting in this regard. So we knew for a while that nitrogen-doped carbon is also active and selective for the CO2 reduction. So we see that there are many groups. I'm just showing you one example where they show a high selectivity towards CO on a nitrogen-doped carbon. They also have supported their observation by DFT, by density functional theory calculations. And what they see is that this triple pyridinic site is most likely the active site for the CO2 reduction. Whereas, for example, if we look at the graphic side, it seems to be that it's not active, or it would have a much, much larger overpotential for the CO2 reduction. So that's why we were surprised when we started measuring blanks. So what we measure as blanks are our carbon electrodes, and in this case, we were using carbon paper. When we do our blanks, what we do is perform the same cyclic voltammetry that we carried out for our catalyst in the presence of nitrogen and CO2. And when we do this in aqueous electrolyte, we see that the current in the presence of CO2 is basically the same as in the presence of nitrogen. So we assume that all that carbon electrodes were doing were reducing protons, right, to form hydrogen. However, when we start looking at the electrolysis, we actually see that there is some CO2 being reduced to CO. But then for the other project, we start working also with acetonitrile, and what we saw was quite different. What we saw here is that in acetonitrile, when we do the cyclic voltammetry in the presence of CO2, we see quite an important reduction current. So this is an indication that actually carbon paper can reduce CO2. Keep in mind that we're going to much more negative potential than what we had in aqueous electrolyte. But nevertheless, when we analyze the product, we see that clearly these carbon electrodes are selective towards CO production. So as one of my students went to do a stay with a collaborator, Dr. Federico Calle Vallejo at the University of Barcelona, he started looking a lot to different possible active sites for the CO2 reduction on carbon. And he came up with these 6 possible sites. We call this the geometric sites. So these are the sites that we have in rings that are not 6-member rings. So 5, 7, and 8. We also have some sites that are vacancy sites, and we have some edge sites. And all of these sites seems to be at least thermodynamically favor for the CO2 reduction reaction at the potential we're working in acetonitrile. So this is showing the ability of carbon to reduce CO2 to CO. Why hadn't we seen this before? So the main reason here is that we have to keep in mind that there is always a competing process, especially when we're working in aqueous electrolytes, so namely the hydrogen evolution reaction. So while there are many sites that could be active for the CO2 electrochemical reduction on carbon, all of these sites are also active for the hydrogen evolution reaction. And if, for example, if we take this vacancy 1, that is the lowest overpotential for CO2 reduction, it also has a lower overpotential for hydrogen evolution reaction. So we never fully realized that carbon electrodes could reduce CO2 because the dominant process was hydrogen evolution reaction. But we should keep in mind that these carbon sites are not completely innocent as we would like them to be. So they are contributing to the reduction current. Maybe if we're working in aqueous electrolyte, they are only contributing with the competing process, but certainly in other electrolytes, they could even be contributing further in the reduction of CO2 to CO. So as I hope I've shown you so far, one of the key challenges to working with this carbon-based material has to do with the heterogeneity of these materials. What I mean by that is that we have a variety of possible active sites. So to really understand the nature of the active site, I think it's important to move to more well-defined systems. And such system could be MOFs, or metal organic frameworks. As you probably know, metal organic frameworks are made of a variety of organic linkers and building blocks that they form an ordered network. These we can choose from so many organic linkers and inorganic building blocks that it gives us extremely versatile material. So we can choose the building blocks to get the properties that we want for these materials. So this is particularly give us important advantages for using these materials in catalysis. So they are versatile materials, they have a high surface area, and they have well-defined active sites because I know exactly what are the building blocks I'm using. So I know the nature of the active sites and I can tune it. In addition, these metal organic frameworks can have redox active sites, and these redox active sites can be useful for electrochemical applications. These redox sites allow to have electrical transport via redox hopping. So what we will have is that the electrons are going from redox site to redox site, while we will have counter-ion diffusion also occurring. So this is not the most optimal mechanisms for conductivity. So we will have a challenge with the low conductivity of MOFs. And then, as we have also seen some issues with the long-term stability of MOFs under electrochemical environments. Nevertheless, there have been some successful examples of MOFs used as CO2 electroreduction catalyst. One of these examples is the MOF 525, which I'm showing you here, is made of a linker, a porphyrin ligand as a linker. This porphyrin ligand can be methylated, so we could generate an active site that resembles those that we believe are the active site on our carbon material. So this is a kind of a great model system for our catalyst. And in fact, there have been some reports of this MOF methylated with iron as a good catalyst for the CO2 electrochemical reduction. So for this reason, we start focusing on preparing electrodes of this MOF to test as electrocatalysts. What we end up finding as the most efficient method to prepare these MOF-based electrodes was to first modify the carbon paper. So we functionalize it to have a carboxylic group that helps as a starting point for growing our MOF. So we grow the MOF directly on the carbon paper, and when we have it grown, we can methylate it with cobalt and nickel. The characterization of the MOF shows that we have grown some MOF particles on the carbon nanofibers that we show here. So we still have this porous carbon paper recovered by the MOF. So this could be useful in different applications for electrochemistry where we have a porous electrode. We also carried out X-ray diffraction, where we see the crystal structure is that of the MOF 525 as expected, and UV-vis measurements confirmed that the MOF was completely methylated. Then we moved to the electrochemical characterization, and for that what we did is carried cyclic voltammetry. We can see the reduction, the redox peaks for the metal centers, so cobalt and nickel. What we observe is that the peak separation of the oxidation and reduction process is quite large. It's larger of what we would expect by the Nernst equation, which is pointing towards a slow charge transfer mechanism. But more interestingly, what we see is that the peak separation for the cobalt MOF is around 214 millivolts, whereas for the nickel is 155. So it's way larger in the case of cobalt. This is a strong indication that this charge transfer kinetics is even slower on the cobalt MOF, and that is dependent on the metal, which we really didn't expect. As a result of this poor kinetics, we see that the peak intensity for the MOFs is different. So in the case of cobalt, we see less, a lower peak intensity than in the case of nickel. And this actually can be seen in the amount of total cobalt sites that are being utilized in the redox process. So we only see 3% of the cobalt sites that we deposited on the carbon paper being active for this redox process, whereas in the case of nickel, we see almost 20%. So there is something that the metal is doing to affect the charge transfer in these materials. So we start looking a lot in the charge transfer mechanism on these two MOFs, and one of the things we did is random Sevic analysis, and I'm showing you this because it's important to confirm that we did have a process controlled by diffusion, which is what we would expect for the redox hopping mechanism. So for the redox hopping mechanism, the charge transfer would be dependent on the hopping distance. So this is this R. So how much does the electron have to do from redox site to redox site, and it's also dependent on an apparent diffusion constant. This apparent diffusion constant is dependent on two things. So one would be the transfer of the electrons, so how fast the electrons transfer from one side to the other, and how fast the ions, the counter ions, diffuse through the MOF. So what are we changing here by changing the metal? So we need to look a little bit more into it. So the ion diffusion is not really affected by, it's not really different in the two materials that we are testing, because basically we have the same electrolyte, so the ions are the same. What is different is the redox nature of the two sites. It's interestingly that the nickel porphyrin reduction is a reduction that occurs, that is centered on the ring, whereas the reduction for the cobalt porphyrin is centered on the metal. This has two effects, and one of which is that the hopping distance for the nickel porphyrin is lower. So this will facilitate a faster charge transfer. In addition, also the electron, so the self-exchange electron transfer between porphyrins is faster for the nickel than for the cobalt porphyrin. So these two will facilitate the charge transfer for the nickel MOF. I don't want to get a lot into these details, but I want you to take home the message that the charge transfer mechanism in these materials is affected by the nature of the metal. And this is important because we usually think that the metal will be affecting our electrocatalytic process by how it binds the reaction intermediates. But in the case of MOFs, we see that it can have an extra effect by facilitating the conduction, charge transfer. So we need not only to think of the nature of the metal for the catalytic process, but also to facilitate the conduction. That's why we chose to start working with this MOF 525 methylated with nickel as an electrocatalyst for CO2 reduction, because it has a good conduction, and it also, as I showed at the beginning, is a metal that is highly selective for the reduction of CO2 to CO, at least in aqueous electrolyte. So what I'm showing you here are some preliminary measurements on the catalytic activity of this MOF, and what we see is that when we add CO2, we start seeing some reduction current. So there is some activity of this MOF for the CO2 reduction. More interestingly, what we see is that the reduction current starts around the potential where we see the reduction of the MOF. And this is also highlighting the importance of working with these well-defined systems, because by having these well-defined systems, we can actually see, we learn more about the active species during the reduction process. However, we still have missing to optimize the preparation of the electrodes and also to fully quantify the products to really get an insight on how this catalyst is working for the CO2 electrochemical reduction. Yet, I think I wanted to show you that this is, although this is new for us, I wanted to show you that MOFs offer an interesting opportunity to be used as electrocatalysts and to really understand the nature of the active site and optimize the active sites. Despite these advantages on the well-defined active sites, we have challenges regarding the low conductivity of these materials. But we see that one of the things that we can do to tune this conductivity, there are many, but one that we observed and we were not expecting was the nature of the metal site. With that, I just want to leave you some final comments. Is basically that I hope that you see the CO2 electrochemical reduction as an interesting process for CO2 utilization. Then these carbon-based materials that we are studying are actually an efficient alternative for this process. But there are still some challenges, and one has to do with actually identifying the nature of the active site. And for that, we will need to move to more well-defined systems. So with that, I would just like to end by thanking my students, especially the ones that did the work that I'm showing you here. So Eduardo did the temperature study effect. Antonio is working in the carbon-based electrodes. On the carbon electrodes, and Denise and Pedro who work with the MOFs. Of course, all of my collaborators, the funding agencies, and you for your attention.
Well, thank you, Ana Sofía, for a very interesting talk. And we have a couple of questions, both from Rosalba Rincon. The first one, she comments that in your cycling voltagrams, why do you cycle at 1 millivolt per second only? And do you see the same trends at higher scan rates?
Yes, the first experiments were done extremely slow. We don't work that slow. We work at 10 millivolts per second now, but it is to avoid some contribution from capacitance. So the slower as we go, we ensure that what we're seeing is mostly Faraday currents. The trends are similar, but it's more clear where we're seeing the start of the Faraday current if we go slower. It's not necessary to work at 1 millivolt. At least we've seen it's not. We work usually now at 10.
Okay, and the second question. Very interesting observation in acetonitrile. How relevant would it be for industrial applications to work in such media?
Depends on the catalyst that you're testing. Of course, for industrial application, people would like to work with aqueous electrolyte because that will be the most beneficial with the environment. We want to avoid working with organic solvents. But there are some catalysts that are still not stable on aqueous electrolytes, so we're studying them in such organic mediums, and we need to keep in mind that there could be some contribution from the carbon, but it's probably not the best option for actual applications.
Okay, we have time for a couple more questions. Salva, thanks you for your answers. Until somebody else may type a question, I have one. You showed for the materials in the first section that you can have this, for example, pyridinic interactions, but you always showed nitrogen metal bonds, and I don't know if you ever considered the possibility of having carbon as potential ligand in those systems, like carbene type or anionic type. Is that something that you consider and something that you could test experimentally?
So it's something that I have not myself. I have not considered them. Other people has proposed that sometimes the metal could be coordinated to some carbon species, and that's certainly possible. I haven't seen, however, anything that is just metal. Carbon doped by metal is usually has some kind of heteroatom that helps the coordination of the metal. But this would be possible, and I think it's probably, as I said, they are so heterogeneous that it's probably we do have them as well, and that is where the challenge is. And so we'll see by studying. That's why I think we need to move to something that we really understand how it looks like structurally, whereas these materials do not.
Okay, and there's no way you could test that then with those materials. Could you test it experimentally to see if you have any?
So we could do some XPS. So we could do some XPS to try to see where the metal is. So if we have some metal nitrogen or metal carbon. So we have done it, but it's not really, sometimes it's not so easy to deconvolute the metal nitrogen, metal carbon and to really quantify it. But that's why I think it's not so simple as it looks like. So I remember doing it with iron, and you have iron oxide, iron nitrogen, and iron carbon. And I really cannot see, but I can tell you it's not iron nitrogen 4 only. It's much more complicated than that.
Okay. Well, thank you, Ana Sofia. Let's see other questions in the chat. So let's thank Ana Sofia again.
Thank you.
Thank you for being part of this, and we will move on to our next and last speaker of the day, which is Professor Ana Flávia Nogueira. She obtained her bachelor's degree from the University of Sao Paulo and her PhD in chemistry from the University of Campinas in 2001. Then she did a postdoc at Imperial College in the UK, and then also was a visiting researcher at Stanford University. And currently she is a full professor at the Chemistry Institute at UniCamp and director of the Center for Innovation on New Energies. Her research focuses on the development of functional nanomaterials and their application in solar energy conversion. She also has experience in the field of perovskite solar cells and quantum materials, as well as dense energy carriers. So the generation of solar fuels through photoelectrocatalytic systems using water, CO2, and other low added value substrates is what drives her research. So with this, I leave the floor to Ana Flávia. Thank you.
Thank you, Van. Can you hear me?
Yes. Yes.
And also see my screen. Okay.
And we can see your top.
Okay, good. I'd like to thank the Chemistry Europe for the opportunity to present the work that we're done here in Brazil, in Campinas. So first, let me show where I'm from. So Campinas is in the state of São Paulo, is the second most important city here in São Paulo. We are located in the southeast part of Brazil. So in Campinas, we have the University of Campinas. Is a very young university. For many years, we were part of this 10 best universities below 50 years ago. But we were just kicked out of the ranking because this year we're celebrating 55 years old. But Campinas is considered one of the most productive universities here in Latin America. And also in Campinas, we have the CINI, the Center for Innovations on Energies. The center is sponsored by São Paulo Science Foundation Agency and Shell. We have about 20 projects in many areas of renewable energy, like photovoltaics, there's energy carriers, I mean, like, for instance, green hydrogen. Also have a program in computational material science. We have at the moment about 280 researchers engaged at CINI, and recently we reached the milestone of 300 publications. The CINI was established in 2018. So follow us in our social media. The website is cini.org.br, because we have now many positions available for postdocs and also for graduate students. So my background is on emerging photovoltaics, Dyson-style solar cells and organic solar cells. But at the moment, we now have other topics of research, as perovskite quantum dots for light emitting diodes, also materials for water splitting and CO2 photoreduction. But the main research in my group is on perovskite solar cells. That's going to be the talk today. So the question is the future renewable? So if you look at this Shell Sky scenario, as I mentioned, Shell is the main sponsor of our center here. 32% of the electricity in 2020 is expected to come from the solar energy, followed by wind and nuclear. So in order to accomplish this 32%, what we need at the moment is a challenge, because we need a solar energy revolution. As everybody knows here, 9% of the market today is dominated by silicon. The processing of the silicon manufacturing is expensive, is very energy consuming. So we need new technologies if you're really thinking about this, in order to couple with this 32% of solar, of the energy coming from the sun. So I think everybody here believes that the merging of the perovskite solar cells was really amazing, because none of the technology so far has reached such a high efficiency in a very short period of time. So if you look here, let me just close some of my screens here, because I cannot see the right part of my talk. Okay, but as you can see here, the efficiency now is about 20. We're approaching actually this the monocrystalline silicon, and we have already passed the polycrystalline silicon. It's really amazing, but we still have some problems. Of course, if you look at this golden triangle, where when we take into account like cost, efficiency, in a lifetime, you see that we're doing very well in terms of cost. We're doing very well in terms of efficiency, but we still have problems with the lifetime. So in my talk here, I'll show some properties of this very exciting semiconductor with that always surprising us in the lab, and some recent contributions in our group using the synchrotron radiation from X-rays to nano-infrared in order to understand more about formation and the composition of these materials. Okay. So the perovskite describes a crystal structure, is the crystal structure of calcium titanate. The generic formula is ABX3, or A is a monocation that can be organic or inorganic, like for instance, formamidinium, methylammonium, they're organic cations, but also we can have cesium, we can have rubidium on A side. The B side, most of the D cations are lead, but also we can have tin or a mixture of them. And different from the oxide perovskites, the metal halide perovskites, they use a light in an X position here. So the most common found perovskite in literature is we call MAPI, is the methyl ammonium lead iodide perovskite, but most of the efficient solar cells are made by combining multiple cations here on the A side, and also varying the ratio between the halide as well. This is an example from my colleague Michael Saliba, where you can see here that when they mix like cesium, rubidium, and formamidinium, so we can achieve efficiencies then higher than 20%, and solar cells with a very high thermal stability, for instance. So this is a list of amazing properties of these perovskite materials. I'll go through some of them. For instance, they're very interesting because we can tune the band gap. You can tune the band gap not only by changing, playing with the cations on the A side, but also playing with the ratio of the halides, for instance. Then you can cover like a very wide part of the solar spectrum. You can go like from the blue to like to the red. This is also very interesting because the absorption coefficient of the perovskite materials is very high. Compare, for instance, with silicon here, that is an indirect band gap. It is even higher than gallium arsenide. It means that, for instance, the device that we're making in our lab now, the thickness of the active layer is just about like 300, 400 nanometers against microns that you have in the silicon. What I mean by the fact that these halide perovskites are considered defect-tolerant material, what does it mean? For instance, if you look at the gallium arsenide, gallium telluride, the traps, the defects are located in the mid gap. Okay, so this that's what we call like deep threads. But when you look at the perovskites, and you see here that the defects are shallow. What does it mean? I mean that the defect levels are very close, or even to the conduction band or to the valence band. It means that think about electron is trapped to this defect level close to the conduction band. Any thermal energy can really remove these electrons and move these electrons to the conduction band. So this is really amazing from this material. And also we can prepare these materials, this metal halide perovskite, in many dimensions. This is an example of the 3D. This is an image of the common perovskite film that you can find in solar cells. But also we can have perovskite quantum dots, as you can see here, like cesium, lead, bromide, very interesting for light emitting applications. You can have some kind of, this is not actually a real perovskite, but you call like a kind of perovskite structure, can be like a molecular or 0D perovskites. And also you can make them like in 2D. In 2D is very interesting because you can make like large 2D structures, like micro size, but also you can have like nanoplates. In the case for the nanoplates, they are also very interesting for light emitting applications. Okay, but we're talking about solar cells. This is basically a simple device. What we have is just perovskite film, where you sandwich between two layers. You have a whole transport layer and an electron transport layer. You generate, when this perovskite absorbs light, you generate electrons in whole pairs. Electrons are moving through the electron transport layer to the FTO, that is our transparent substrate, and holes are moving through the whole transport material to the gold contact. The most common whole transport material in this configuration here that we call like NIP is the spiral. But also we can use these perovskites, these metal halide perovskites, also in light emitting diodes, lasers, X-ray detectors, and so on. This is one of the most efficient devices that's from the group of my colleague Juan Pablo Correa. Juan Pablo is from Colombia, but he's now in Georgia Tech. So they prepare a very nice tin oxide electron transport layer, as you can see here, using a combination different organic cations on A site. They were able in the lab to achieve more than 25% efficiency. So, and what we're doing in Brazil and why we're using the synchrotron, and here I'm going to do some publicity, because in Campinas here, we have the synchrotron lab. It's part of a really big complex here. So this was on the left, it was the old machine. The operation was closed in August 2019. But now we have the new synchrotron, It's the second 4th generation synchrotron in the world. We have the IMAX in Sweden, and now we have the series in Brazil. The beam lines are under the technical and scientific commissioning, but some of beam lines are already open, so are open for submissions. So that's my point here is I'm really encouraging scientists in Latin America to really submit proposals to the synchrotron here. This is a photo of the inside of the series. It's really amazing to visit this lab. So what's interesting from the synchrotron is because we can combine in situ and operando experiments with synchrotron light. Not only X-rays, but also the infrareds I'm going to show here. We have been done many work in collaboration with the synchrotron in terms of looking at the perovskite. So I won't have time to go through all of this. I'll focus today how the synchrotron, how the in situ experiments coupled to synchrotron radiation can help us to understand the formation of the perovskite films for solar cells. So to prepare this film is very easy. It's just mix like lead iodide and methylmonium iodide, and then you have MAPI. MAPI, as I mentioned, is the most common perovskite. So there's a beauty of this technology because you can start from chemicals with like low purity, no higher than 90%. The chemicals are cheap, even the deposition methods of these perovskite films are cheap. So let me show here one of the most used methods to prepare this perovskite. So this is what we call like solvent engineer methods. This is why. So this is my postdoc. She's depositing a solution containing the precursors, lead iodide, methylmonium iodide. So she's using a spin coater. So there is a very critical step now. As you can see, she's going to drop a chlorobenzene. That's what we call like a solvent. Can you see the change? I think you can see, you can visualize the change in the color of the film as soon as she drops this the chlorobenzene. Then at this moment, you have the formation of the perovskite. So you see that this difference in color. So this is most used method. And what you can think about it, we are using chemicals with low grade. We are using like ink to prepare like more than 25% solar cells. So of course, there are some consequences when you use this very cheap method to prepare these films. So what you want is at the end, you want the cubic perovskite. This is the structure that you have. But always, yeah, you end up also with some hexagonal phases. You also will form these hexagonal phases. They are actually more thermodynamically more favored to form these hexagonal phases. And why you don't want these hexagonal phases? Simply because, as you can see here, the octahedra, they are actually not connected to each other. So the mobility is low. So all of these yellow phases, they have like a very high band gap. So they're not suitable for a photovoltaic application. And then we decided to track the formation of this perovskite film, the cubic perovskite film, using the synchrotron here in Brazil. The technique was that we chose, it was the GWOX, grazing incidence, wide angle X-ray scattering. So here you have your perovskite film. So this is your X-ray beam, and this is your detector here. This is what we call like 2D detectors. This detector is very interesting because they allows you to collect many you have a really fast acquisition of the data. So it is only in the synchrotron that you can actually do in situ experiments. So basically, this is that we have. This is the diffraction signal here. So we managed to insert. We managed. This was this student. We managed to bring the spin coater from our lab. We put on a beam line. We built this box here. This the X-rays coming from this side. This is a spin coater. The film is here. This is our 2D detector. We built this box where we're able to control the atmosphere inside of this box, and also we are able to control the time to deposit that solvent. I'll show you some of the some examples here, some of the results. So we use these perovskites here containing cesium and formamidinium. So this is the data that you can plot. You can plot Q as a function of the time. Remember that Q is related to theta. Okay. So then in the beginning of the spin coating, this is the signal that you have here, the signal from the solution. Then as soon as you drop the solvent, you start to see the formation of the perovskite. So the signal at 10 nanometers -1 is the signal from the cubic perovskite, so the phase that we really want that to form. But also, as you can see here, we also have the formation of the hexagonal phases. Very interesting, because as you have really fast acquisition, you can do these experiments with time. You can plot the intensity of these diffraction peaks with time. As you can see here, you see that first you have the formation of the hexagonal phases, and then the hexagonal phases are converted to the cubic perovskite. And also we check the time to drop the solvent. As you can see here, this is the result that I showed you before. So after 15 seconds, we drop the solvent. We end up with a very nice morphology and a film with like a lot of, I mean, most of the phase here is actually cubic. But when it takes some, if you drop the solvent too late, this is what you have. You don't have really have a really bad morphology, and you can even like identify the signals from the cubic perovskites. Have also the formation, a mix of hexagonal phases and a mix of intermediates. So this is it is a really manual step. Okay, so more recently we are moving to this deposition to using a blade coat deposition. What's a blade coat deposition? As you can see here, I'll play the video. This is the solution, the same precursor solution, but I'm using a kind of knife to spread this film over the substrate. And instead of dropping the solvent here on the head of this knife, I have a flux of the nitrogen. So in this technique, I can really exclude the use of toxic solvent, avoid the saturation of my glove box, and this kind of deposition is more scalable. So as you can see here, is really quick. In seconds, you can just have a very nice, very transparent film of perovskite. So what also we did in this project was like we deposit all of the other layers also using this technique, and achieve like an efficiency of 14%. When you compare these both two methods, then we are back to the synchrotron in Brazil. This is the results that I showed you before. Then we go back to the synchrotron and we did the same experiments, the synchrotron, but now using the nitrogen. So as you can see here, if you compare both results, you see that in the case of the nitrogen, the formation of perovskite is lower. Okay, you see a lot of also the formation of the hexagonal phases. Again, we have the conversion. First, you form the perovskite, the hexagonal phases, and then they are converted to cubic perovskites. But the question here with the gas quenching, the crystallization is much lower. And in fact, today we have the record of 21% in our lab, and the reactor is done using this technique, because also we can the crystals that you can obtain using this technique is much larger. So just to finalize here, one of the questions like, okay, using all of this in this technique, we're able for the first time in the literature to actually propose the mechanism of the formation of this perovskite. It's very complex because it depends on the composition, depends on the atmosphere, for instance, the humidity, depends if you use or not a thermoannealing. So it's a very complex, but everything starts with these hexagonal phases. And the question was, okay, but even at the end of this process, do we still have these hexagonal phases in the film? Because we don't want them. And if they're still in the film, can you see them? Can you find them on the film? So also using the synchrotron, now another beamline. Now here using the nano-infrared. The nano-infrared, as far as I know, is going to be open for submissions now in the next month. So here we combine AFM. The AFM acts as a kind of antenna. And also we combine the AFM with the infrared from the synchrotron with a resolution of 25 nanometers. So from using this technique, you have basically two results that you can obtain. You can obtain what we call like a broadband image of the film. And also we can also get some what we call like point spectrum. I'm going to show here these two results. So this is normal SEM image of the perovskite film. So here on the left you have the normal the AFM topography. Here on the right you have this what we call like an infrared broadband image. So what is interesting here is the same crystal here. If you look at this crystal here, you see that the intensity of the infrared light is different. What does it mean? Because what we know from this technique is like the organic part of the perovskite, those organic cations are absorbing the infrared light. So what we see here, because the difference in intensity, you see that the perovskite grains are really unhomogeneous in compositions. What I believe that close on the grain boundaries, we have a depletion of these organic cations. But also, as I mentioned, you can also collect point in spectrum. For instance, you can select, this is again the EFM on the left, the infrared broadband on the right. This is with a higher modification. For instance, you can choose the grain that you want, and you can get a single infrared spectrum of the grain. In this case, we are following the stretching of the ferromagnesium cation, and for the first time, we were able to see that these greener grains here are in fact the hexagonal phases. So these hexagonal phases are also well distributed in the film. So with that, I want to approaching the end of my talk. Some important remarks here is that the perovskite materials, they have extraordinary properties, but also these materials are very complex and stable, and some properties we still need to have a much better investigations. So this is nice to have so many, it's still open for studies. So the formation of the perovskite is really complex. It depends not only the composition, the solution, but also depends on many parameters, and also all of things gonna affect the device efficiency. So this is really important to understand more about the perovskite formation. Not less important, all of these phases that are more thermodynamically favored to form, we need to try to control them more, because also recently we demonstrated that also these hexagonal phases are the first phase to appear when the beginning of the degradation. So really need to study more these hexagonal phases and avoid them. And I hope that I have show you here that the in situ and or synchrotron radiation can help us in somehow to elucidate some of these problems. And here is my advice. So the synchrotron is here in Campinas. It's an open facility, and we're looking for submissions from our colleagues here in South America. With that, I'd like to thank you very much for your time. And also, of course, I need to thank to my group and also my collaborators in the synchrotron and my funding agencies. Thank you very much.
Thank you, Ana Flávia, for a very nice talk, and also thank you for the offer. So maybe I could start asking about the logistics. I don't know how complicated it is to submit a proposal.
It's really easy.
Mm-hmm.
It's really straightforward.
So it goes through just a page and you don't need necessarily a collaboration with somebody in Campinas to go ahead with this?
No.
Okay.
No. In the past, we used to pay for the accommodation for the Latin American researchers, but not anymore. Yeah, okay. Yeah. And also there is a hotel inside of the CNP, the complex.
Okay.
So, okay. Yeah, you also can fly directly to Campinas. There is an international airport here.
Yeah, Viracopos, I think, is the airport, right? Yeah. Okay. Well, we have a question here from the panel. From Yi Yang. Thank you very much for an interesting presentation. I'm wondering here if oxide-based perovskites with formula AB03 can be made as film for solar utilization.
Well, I'm not so familiar with this oxide perovskites for in terms of like as like a TV area, because the band gap, all of these oxide perovskites are really on a UV, they have like a, but also they can be used as an electron transport layer. This also can, and it also depends on the conductivity, but also can use them as electron transport layer. but not as active layer because of the band gap. But also this oxide perovskite, a lot of people are using as a photocatalyst.
Okay, thank you. Are there any other questions? Please go ahead and type, don't be shy. Well, I don't see any more questions for the time being. No, in that case, well, thank you again, Ana Flávia. And well, let's welcome back Sandra for final remarks.
Hello, thank you very much to all of the speakers for these very interesting talks and for joining us today. Thank you, Ivan, for helping us to moderate this very interesting session and for your continued support of Chemistry Europe, in particular of the European Journal of Inorganic Chemistry. And with this, well, I close this session without missing the opportunity to invite our audience to visit the web pages of Chemistry Europe journals to see the Latin American science that is being produced currently in the several special collections that ChemCatChem, EurJIC, electrocatalysis, EurJIC have published. And I take also the opportunity to announce 2 upcoming special collections that will be published by ChemCatChem and ChemPhysChem. So just stay tuned for further information. Goodbye.